Let's talk about another type of question you might see. These are called closest distance problems. And I want you to think about this picture. You should have this in your notes. And let's imagine that this describes some ship sailing in the water. This isn't really a mountain. This is like a bird's eye view of what's going on here. So here's the water. Let's put some waves in this, make it look like a real ocean. Ah, yes, this was reminding me of my time in Florida. And then here's land. We might even put a tree in here. Why not? We'll have... or let's put some bushes, right? So here's like a little bush here, and then here's a little bush and we have this land mass, and somebody's looking out from point P, and here's a ship that's going by. It's sailing through point A in the direction of B. So B is like my direction vector of motion, and I'm going in this direction. Here's my port, P. I want to know at what time will the ship R be the closest to the port. So if we're moving in this direction, I want you just to think a little bit. If I continue in this path, at what point in this path am I going to be closest to P? So think about that. Right now, where I begin, I am this far away from P. As I continue to move on and on and on, R is this far away from P. At what point on this line in the direction of travel will I be closest? Think about that. Hopefully what was coming to mind was a perpendicular line. This is the closest I will ever get to point P as long as I'm traveling in this direction. So how do we relate this to vectors? Well, when PR, this PR is perpendicular to this AR, we can talk about the dot product, right? We know how to find perpendicular vectors. If vector PR dot the direction vector of my motion is equal to 0, then the scalar product must be 0. Therefore, these must be perpendicular. So let's keep that in mind. Perpendicularity and dot products equaling 0. So here's a beast of an example. I want to find basically, a few things. I've got this graphic, once again, we're at C. Here's the land. Something is moving out of C. And we want to, let's kind of read through this. Measured in distances are measured in kilometers. This ship is at R. It's right here. This is the position at point R. And it is moving in this direction, 3, 4, at a speed of 10 kilometers an hour. Now, one thing I want to point out is this is not my velocity, right? It says moving in the direction of 3, 4. So that's not my velocity vector. This says it's a speed of 10, so this is going to be the magnitude of my velocity vector. So we're going to kind of have to use those two facts together in just a second. I want to find an expression for the position of the ship, not the position vector, but the position of the ship in terms of t, where t is the number of hours after leaving port A. So we kind of started here and left in this direction. So let's attack letter A first. The general form of my vector equation is going to be R equals A plus time t times the velocity vector B. So right now, for this vector B, this velocity vector, we have a direction and magnitude. So we have to put those things together to figure out what the actual velocity vector is. What do we know? We know that the velocity vector, whatever it is, Vx, Vy, is going to equal some scalar times that direction vector that was given before, 3, 4. Right? So the velocity is going to be, it's parallel to this direction, 3, 4. I just don't know how much I'm multiplying this 3, 4 by to get my velocity vector. But I do know that the magnitude of my velocity, which is my speed, is equal to, what did I say it was? 10, right? Yeah, 10 kilometers an hour. And that should equal the magnitude of this whole thing, or k times the magnitude of my direction vector, 3, 4. And so this is going to be 10 is going to equal k times the square root of 9 plus 16, which is equal to 25. Square root of 25 is 5. So 10 will equal k times 5. So k must equal 2. How does that help me? Well, if k is 2, then my velocity vector is going to equal Vx Vy is going to equal 2 times 3, 4, the vector 3, 4. So my velocity vector is 6, 8. All that work to find my velocity vector. I'm not even done. Really what I've started is I've just found the b in this vector equation. I want to find the position of this thing. So if we keep going forward, let's change up the color here to green. The position at xy is going to be given as, this is like my a, r, my resultant vector is my position vector xy. A is going to be my initial point. My initial point is negative 8, 3, as given by this, plus t times my velocity vector, 6, 8, which I just found. So the position at r is going to be, let's smush all this together, my x component is going to be negative 8 plus 6t, and my y equation, or y component, will be 3 plus 8t. So all of that just to find my position at any time t. So if I said we are 3 hours in, I'm plugging in a 3 to these t's, and I can figure out just exactly how far away I am. So that was A. Let's do B. I want to find the time when the ship is closest to port P. So let's again think about this. When I'm going to be closest when this line is perpendicular to this line. So I want to know when is R here. That's what I'm interested in. I want to know when the vector PR is perpendicular to the direction vector 3, 4. And I find that another way of saying that is I want PR dot 3, 4 to equal 0. So we kind of have to figure out what PR is. So let's recall what the R position is. Or actually, let's write down what the point P is. P is at 10, 2. And R is from the last part of the problem. We had negative 8 plus 6t, comma, 3 plus 8t. So if I want to find the vector PR, I need to begin at P and go to R. So that means vector PR is going to equal negative 8 plus 6. This is my vector R, or my position R, excuse me, and 3 plus 8t. And what I have to do is I have to subtract the point P to find my vector PR. So this is minus 10, and this is minus 2. So this is like my point P. So I took R, subtracted P, to find the vector PR, which is equal to, that'll be negative 18 plus 6t and 1 plus 8t. All right, so that's vector PR. I want this vector PR to dot with 3, 4, and I want it to equal 0. So now I just have an algebra problem here. So I'm going to take, let's squeeze this down here. Negative 18 plus 6t, 1 plus 8t, dot 3, 4 should equal 0. So the dot product will be expressed as 3 times negative 18 plus 6t plus 4 times 1 plus 8t. That should all equal 0. So let's do a little bit of algebra. This is negative 54 plus 18t plus 4 plus 32t equals 0. Let's combine our like terms. This is negative 50 plus, that'll be 50t equals 0. And see, I think I have just enough room to squeeze this out. This is going to turn out to be 50 equals 50t. So t equals 1. What does that mean? 1 hour after leaving point A is when I'm closest to the port P. Whew, that's a lot of work. So make sure that you kind of rewatch this if you need to. But this all kind of hinges on the fact that the dot product of perpendicular vectors is equal to 0. So for one final problem for you to try, a whole bunch of stuff, draw things out, that's going to help you, but this is going to be a lot like the last problem. So pause the video and work through this one, and then resume when you're ready to see the answer. All right, so here's my solution for this UTRI problem. Hopefully you got something like this, and thanks for watching.